functions are the simplest functions, and they look like this. Okay, so if it's y is a function of x, what kind of function is it? It's a function that looks like this, mx plus b. Okay, so m and b here, we might call them constants or parameters. Sometimes it really bugs people when we say that m and b are constants, because you might be thinking, well, they're variables, right? Why are we calling them constants when they seem like they can vary? You're not wrong about that, but in the context that we're looking at here, because x and y are the variables we're interested in, they're the kind of the real variables. Okay, so another way to think about it is what we would do if we're thinking about a particular linear function is we would pick particular values of m and b. Okay, so if we had m equals 5 and b equals 3, that would give us one particular linear function, y equals 5x plus 3, or m equals negative 4 and b equals 0. That would be y equals negative 4x. Okay, so they could take different values, but we're going to be treating them as values that aren't changing while we're thinking about the relationship we care about, which is the one between x and y here. Okay, so linear functions can all be written in this particular form here. As the name implies, if you graph this function, plotting as we usually do the x value on the horizontal axis and the y value on the vertical axis, this will indeed look like a straight line. We'll get to some pictures in a minute. And the other cool thing about these parameters, about these constants, is that they both have interpretations that we might care about. So the interpretation of m is the slope of the line, and b is the, call it the intercept. It's where the line intersects the vertical axis. Okay. So let's just look at an example here. So here I've got an example of a line. The line, I'll try and highlight it in purple here without making it too wobbly. Here's everything else is just axis and all that. Here's my line, and the equation of this line, I'm going to assert, and then we'll convince ourselves, is y equals 5x plus 1. So I'm saying here that this is a line that has m equal to 5 and b equals 1. Okay, well, b is kind of the easy one to check. Let's just look. So I'm asserting that b is where the line hits the vertical axis, and indeed it does hit it right down here at 1. And that makes sense, because what's going on at the vertical axis? That is the value where x equals 0. Okay, so f of 0, okay, where x equals 0, we're not going any direction in the horizontal, on the horizontal axis. The y value is 5 times 0 plus 1 gives me 1. Great. And the other thing that I've asserted, and I think we can see here, is that I'm saying that the slope is 5. Okay. Things about slope. I'll use my kind of definition color for today. Definitions are in blue. Slope, ooh, that's too messy. Use a thinner line. So slope, you might have learned a phrase that slope is rise over run. That's one way to think about it. You might have thought about it as the change in y over the change in x. And really, Slope, in terms of thinking about functions as relationships, slopes are what we usually want to know if we want to know how does X affect Y. Okay, how does X affect Y? One thing we want to know is the effect positive or negative? As X gets bigger, is Y getting bigger or smaller? Okay, in this case, we can just look at the line and say, okay, that's a positive relationship, and we can also see it from the fact that we have a positive slope here. The other thing we want to know is the relationship between X and Y big or small? That's hard to tell without knowing what units are, but that looks like a pretty steep line. So you might say that's, if these units are sort of roughly comparable, that's X is having a pretty big effect on Y. We go a little way in the X direction and it corresponds to a big change in Y. Okay, so let's look at that in the picture here. So to calculate slope or to see slope, to understand slope, we are thinking about changes. So you have to have a starting value and an ending value. Let me back up a minute and draw your attention to these triangles that I drew here. Those are capital Greek letter deltas, is what they are. And delta is conventionally used throughout math, science, social science to represent a change. So we might actually also write this as the change in Y divided by the change in X. And how do we represent those changes? Well, we can represent it as if we have 2 points, x1, y1, and x0, y0. We just take the differences. Okay, so the change in Y over the change in X, or delta Y over delta X, any of these things all equal y1 minus x1 divided by x1. Wait, I think I just said that wrong. Y1 minus y0, I wrote it right, and so the difference in the y's, the change in Y on the top, the denominator is the change in X, it is x1 minus x0. Okay, so you might think of it as an ending value minus a starting value. Doesn't really matter which one is the ending value or the starting value. These are all different ways of talking about, thinking about calculating slopes. And again, you think about, like, what do we want to know about a function? You might think of, for a unit change, we go one direction in X, what kind of impact does that have on Y? So let's do that in the picture here. Let's start off maybe at the intercept. We can start off any place we want, but that's a fine place to start. We start off here at X equals 0 and Y equals 1. So I'll put that point here. Oh, this is something else I just wanted to mention. If you've been away from using graphs for a while, the convention is we always put the horizontal coordinate first. So this is my 0 is my X value and the vertical one next. Okay, so X's come first, Y's come second. So this is 1 point on my line. And if I go 1 unit, goodness, I'm using all my colors today. So I go 1 unit in the X direction. Okay, so this is a delta X equals 1. So I'm going from X equals 0 to X equals 1. How far do I go in the Y direction? Ooh, I go a long ways. I go from 1 here all the way up to 6. Okay, so another point here on the line is X equals 1, Y equals 6. Okay, so the change in Y that corresponds to this 1 unit change in X, this whole amount here, delta Y, is 6, my ending point. Okay, my ending point here minus my starting point. 6 minus 1, it is indeed 5. Okay, So just so I'm not doing anything that looks like smoke and mirrors here, for this particular function, the delta y over delta x is 5 for 1. I really need to make my screen stop doing that. Makes us all seasick. And that is indeed the slope. Okay, that picture got nice and colorful. Let's kind of keep in mind the purple line here. Again, what do we want to know about functions in general? We want to know what kind of effect x has on y. Is it positive or negative? Here it's positive, as x is increasing in the sense of going in the positive direction. Y is also increasing, and it's pretty big effect. Okay, so now let's look at a different line here. And again, I'll kind of try to sketch in the function here to distinguish it from the background. Okay, and so this is a different function. We're picking different values for m and x. So here we have y equals -1/5 x plus 1. I'm asserting that, but let's, you don't have to believe me. Let's check. So again, the b equals 1. That's saying that when x equals 0, this whole term equals 0, so we just have y equals 1. And indeed, when x is 0, y does equal 1. So good. We've got x equals 0 and y equals 1 is a point on this line here. But it is a different kind of effect, right? We look at the slope, we just look from the picture and say, oh, that's a negative effect. Now, as x is increasing, y is decreasing. Okay, so as we're going towards the positive direction for the x's, we're going towards the negative direction for the y's here. It's also not much of an effect, right? We go 1 unit on the x direction and barely anything in the y direction. Okay. I might just want to calculate the slope to convince myself that this -1/5 is right. Remember, if I'm going to calculate slope, I can do delta y over delta x, and I can pick any 2 points that I want. So I've got this 0, 1. That seems like a nice point to start with. Another point that just sort of seems convenient is right here. I can tell that 5, 0 is a point on the line here. So let's have this be my starting point, x0, y0, and this one be x1, y1 here. So when I do delta y over delta x, it's y1 minus y0. And what does that mean in this context? It means y1 is 0 and y0 is 1. That came out. I didn't mean to use the opposite values for the indices, but that's how it came out there. Okay, so I've got my ending value for y and my beginning value for y, and my beginning value for x then is 5, and my ending value for x is 0. 5 minus 0, that is indeed -1/5. And yes, if I made 5, 0 the starting point and 0, 1 the ending point, I'd still get -1/5. If I picked any 2 points on this line to calculate the slope, I would get the same answer. That fact that the slope of a line, how much x affects y, and whether it's a positive or negative effect, is the same with a linear function, the fact that it's the same no matter where you are in the x's, that is both kind of the best thing and the worst thing about linear functions. It's really nice and simple. We want to know how much bang for the buck we get, so to speak, from a unit change in x. All we have to do is find 2 points, calculate the slope, and it's going to be true no matter what value of x we pick. Nice and simple. On the other hand, do we think the real world is like this? Do we think that the effect of campaign funds on likelihood of winning an election is linear? That the effect of going from $10,000 to $20,000 is the same maybe as going from 100 to 110,000? I don't think so. Okay. Many of the things that we're interested in studying don't have as simple of a relationship as implied by a line. Okay. And one of the reasons why we're learning calculus in Poli-Sci Math Camp is because calculus helps us calculate something like slopes for functions that aren't as simple as just plain lines. That's where we're going. Is there anything else I want to say that I haven't said? No, I think that's pretty much all I want to say about linear functions today. Oh, there is one other thing. I had a feeling there was something that I was leaving out. The one last thing I just want to show you is that sometimes linear functions will sort of be lurking in an equation, and you just got to recognize them. Okay, so if we start with something like 2x minus 3y equals 6, that's not the y equals mx plus b form, but could we rearrange it to fit that form? We sure could. Okay, so just my observation here is this is not exactly y equals mx plus b, that's an x there. But let's just do some algebra to get y by itself, and indeed we'll be able to find that. So subtracting x and adding 3y to both sides, I get this. So I'll end up with 2/3 x minus 2 equals y. Okay, so in general, when you have functions or equations, I guess there's a function kind of implied here, but it's not written in a form that we would necessarily interpret as a function. But when you have equations that apply a relationship between x and y that doesn't involve anything fancy, no exponents, no logarithms, no multiplying x and y by each other, none of that crazy stuff. It's just x being multiplied by a number, y possibly being multiplied by another number that we can algebraically isolate, another number that might be added onto it. There's a linear function implied. Yeah. Okay. So just to reiterate the earlier point, the fact that the slope of a linear function is the same no matter where you are in terms of your values of x and y is both an advantage and a disadvantage. You're going to be working with linear functions and linear relationships throughout your methods classes because sometimes that simplicity is really helpful, and sometimes it's just honest, since we don't have enough data to understand anything more than a linear approximation of what we're thinking of, but it's also very limiting from a point of view of the kind of theoretical questions we want to ask. So we're going to be moving in the next lessons, the next units, to think about functions that represent more complicated relationships than linear ones.